Hello students, welcome back to another video. In today's video we'll be doing some questions of light waves. Question number 6 is saying figure 6.1 shows how an object placed in front of a plane mirror M. This is a mirror, this O is the object. Two rays from the object to the mirror are shown. So there are two rays that are emerging from object and hitting the mirror. Part 1 is saying on figure 6.1, for one of the rays shown, draw the normal to the mirror. So we have to draw a normal on the mirror, and you know that normal is always 90 degree to the plane of the surface. So I'll put on my protector, place it on the ray wherever it's falling, and I will draw a 90-degree angle to the plane of the mirror, and this is supposed to be my normal. Next part of the question is saying that mark the angle of incidence and label that angle as x. So in our diagram, this is incident ray which is falling on the interface of plane, and whatever angle it is making with the normal is the angle of incidence. Part number 2 is saying draw the reflected rays for both the incident rays and construct line to locate the image. Label the image as I. So we have to draw reflected rays and also we have to place image. So incident angle is equals to the reflected angle. I will measure the angle of incidence with the normal with help of protector, which is I guess 44 with the normal. So I will draw the same angle with the reflected ray as well. And for the other ray, I will again measure the angle of incidence of the incident ray with the normal, and I will draw the same reflected angle on the other side of the normal. After placing these two reflected rays, these are two reflected rays, and now this is the normal and this is the angle of incidence. Now to draw the image, the thing you know is that for an image made by a plane mirror, it is always same distance from the mirror as the object is. So if the object is 15 boxes away, so the image would also be 15 boxes away from the mirror. You will extend your reflected lines, and you will see wherever these two extended lines will meet would be your image, and it would be exactly at the space at the place I have spotted. See, so this eye point is the image of the object and I am naming it I. Question number 3 is saying figure 7.1 represents an object placed in front of converging lens. Question number 1 is saying state a full description of image I. So the I arrow is the image and the O arrow is the object. You can see that the image is magnified or larger than the object. The other thing is that the image is made from not from the actual meeting of the rays, but they are extended to meet, so it's a virtual image. And the third thing is that object is upright, image is upright, so the image is erected or upright. B part is saying use the letter on figure 7.1 and identify the focal length. So if you see, our case is this one, object between F and the lens. And for this, we can see that the image is formed by extending the rays. So this is a virtual image, enlarged image, and upright image. You can see that the ray which is parallel to principal axis passes through the focal length of the lens, and the other ray which passes through the center of the lens goes undeviated, and when you extend these lines they meet at a point and form an image. Similarly, this is a ray parallel to principal axis and it will pass through focal length of the lens. That means this S point is the focal length of the lens. So I am writing S is the focal length. The B part is saying that figure 7.2 shows an object placed to left of the converging lens. A principal focus of the lens is at the position marked as F. So f is the focal length of the lens. Part number 1 is saying draw two rays to locate the image of the object and draw the image, and draw one other ray from upper tip of the object O to the image. So firstly we'll just measure the focal length. By placing the mirror over here, we can see that the focal length is 3.5 centimeter. So I will mark the focal length this side as well, and I'll put a mark on 3.5 centimeter and will name this point as F. Again at 3.5 centimeter, I will mark 2 times of focal length, that means double focal length. So our object is beyond 2f. So this first picture is our concern, in which object is beyond 2f. And in this picture, the rays that are parallel to principal axis are passing through the focal point, and the rays that are passing from the center of the lens are going undeviated. So we'll draw the same pattern in our question. The rays that are parallel to principal axis will pass through the focal point, and the rays that are passing from the center of the lens are going undeviated, and the point where the both rays are meeting is the point where our image would be formed, and this is our final image. Question number 6 says a page of printed text 18 centimeter from converging lens of focal length 35 centimeter. Figure 6.1 is a scale diagram of arrangement with each of two principal focus of the lens labeled as f. So here we have a lens. A printed page is placed 18 centimeter in front of a lens, and focal points are 35 centimeter away from the lens. So 35 meter this side is one focal point, and 35 meter of the lens that side is also another focal point. A length of 1 centimeter on a scale diagram represents an actual of 5 centimeter. By drawing, locate the image of the page produced by the lens and label it I, and determine actual distance of image from the lens. So again, the case is the same, object between focal length and the lens. The line which is parallel to principal axis will pass through focal length, and the line which passes through center of the lens goes undeviated, and you extend your lines to make the image. Going to the question again, I will draw a line which would be parallel to principal axis, and this line will pass through focal point of the lens, and the line which passes through center of the lens goes undeviated, and when you extend these lines, they will meet at the point, and you'll name that point as I, and this point will make your image. And you can measure that this image is approximately 38 or 38.5 centimeter away from the lens. So we have locate the image of the page, and we have labeled it I, and we have already measured the distance of the image from the lens, which is 38.5 centimeter. You can have any answer between the range 35.5 to 38.5 centimeter. Next part is saying converging lens can be used as a magnifying glass. State whether the image produced when the lens is used as magnifying glass is a real or a virtual image. A converging lens acts as a magnifying glass when the object is between lens and focal length, and you can see the image produced is much larger than the object, and the image is not produced by the actual meeting of the lines, but we have extended our rays to make the image. So this is a virtual image, and the rays do not actually meet and seem to come from the image. Next part is saying suggest how someone who is long sighted may benefit from a converging lens. So how converging lens helps someone who has a problem of long sightedness? A long sighted eye form image behind the retina, that's why it's blurry. So this convex lens reduces the focal length of an eye and produce the image exactly on retina, so it can be a clear image. Question number 4 is saying the refractive index N of the glass is 1.5. Part number A says state the equation that relates speed of light in the air, the speed of light in the glass, and n, that is refractive index. So the definition of refractive index says that it is speed of light in the air divided by speed of light in the medium. The medium can be any medium. In our case, it is glass. So the refractive index of glass is 1.5. You can also write it in terms of Vs and Vg. I have just wrote the general form so you can consider it well. Part number 2 is saying the speed of light in air is 3 into 10 raised to power 8. Find the speed of light in the glass. Using the same equation again and arranging it with respect to speed of light in glass, putting in the values, refractive index of glass is 1.5. So I have wrote 1.5 over here, and the final answer is 2 into 10 raised to power 8 meter per second. B part is saying light traveling in glass strikes the edge of glass. So figure 6.1 shows a ray of light at an angle 41 degree to the normal. So this is a glass and this is air. There is a ray coming which is hitting the glass and making 41 degree with the normal. The light passes from the glass into the air. Calculate the angle that the ray makes with the normal in the air. For this, we can use Snell's law. Refractive index of first medium multiplied by sine of incident angle is equal to refractive index of second medium multiplied by sine of refracted angle. Glass is the first medium and air is the second medium. So I'll plug in the values. 1.5 is the refractive index of glass multiplied by sine of angle 41 because incident angle is 41. Refractive index of air is always 1. So I'll put 1 over here. And sine of refracted angle which we need to find. Arranging all these with respect to refracted angle because we have to find the refracted angle. And 1.5 multiplied by sine of 41 degree. I will take sine to the other side and it will be sine inverse on that side. Sine inverse times 1.5 times sine 41. Plug in all these values into your calculator. Your final answer would be 80 degrees. Thanks for watching the video. I have attached the link of PDF in the description as well. If the video was helpful, please hit the like button and subscribe my channel.